Hey there. All right. I hear you standing. I think you're muted, Richard.
I am no longer muted.
All right.
I am unmuted now.
All right.
You know, what is it? 2.5 years of sitting here messing around with Zoom, and I still can't remember to hit the unmute button.
Yep.
I think that it's a common affliction.
Well, I hope everybody's doing well.
Yeah.
It's been a month since the last time we met, but we are up here at the Chabot Space and Science Center inside the observatory, housing our 36-inch reflecting telescope, the one we call Nellie. And we have reasonably good weather tonight, so we're going to be able to look at a few things with our telescope. We've got 2 cameras on the telescope right now, so I think we're going to start out with the Great Orion Nebula, which is a star-forming region in the constellation Orion.
Well, before we do that, let's make sure we introduce ourselves. So,
yeah.
Speaking to you was Gerald McKeegan. I'm Rich Ozer, and we have Rick Taft with us tonight as well.
In the dark.
In the dark. I'm kind of in the dark and in the grain.
Yeah, I'm very
grainy.
I'm in the grain. I'm in the grainy universe.
I'm kind of grainy too.
Yeah,
here.
You're grainy too. Rick is in the sharp but dark universe.
Right.
I do want to mention that unlike many previous months, the Chabot Space and Science Center has reopened for Friday and Saturday night telescope viewing and for weekend access to the Science Center and exhibits. So check the website, chabotspace.org, and you can get details about hours, admission fees, and the various programs and activities that we have going on here every weekend now. Also want to mention that next month we'll have a First Friday event, which is, Gerald, what's the date on the First Friday?
What is it, the 5th of February, I believe it is?
Yeah, I believe it's February 5th. That's correct. And
it's either the 4th or the 5th. I can't remember which. Whichever Friday that is.
Whatever Friday it is. There's only one that week.
Yeah.
It's actually the 7th. No, it's not. That was January. Take that back. It's Friday the 4th.
All right. Yeah, I kind of suspected that.
So that'll be a First Friday event, and that gives people admission to the Science Center, planetarium show. There'll be a Zeiss show that night too, won't there?
Yes, we are going to have a Zeiss planetarium show that night. Right. And I'm not sure what all the other activities are going to have, but
well, the Telescope Makers Workshop has reopened as well. Yep, we're going to be holding our first one this coming Friday night. That's tomorrow night, and we'll be open First Friday as well, and all the other weekends, all the other Fridays as well, assuming knock on wood that we're able to remain open and that county and Chabot regulations allow us to do so.
Yeah.
Okay, so everybody stay well. That's all I got to say.
Yeah, if you do plan on coming up for First Friday, be aware that you will have to show proof of vaccination when you come in. So that's a new city or county requirement. So we all have to put up with it.
Yep. And so, remember that. Go ahead and download it to your phone or take a picture of your card and bring it on your phone, and that will suffice. All right. Well, that's it for announcements. I do also want to mention that we appreciate all of our donors and all of our sponsors, including Fremont Bank. Those of you who are watching on Facebook, you'll notice that there's a donate button on the live stream, and we'll appreciate any donations that we can get, as well as any memberships, if you're interested in becoming a member of the Chabot Space and Science Center. All right. Well, that's it for the commercials.
All right.
Great.
Well, Rick, I think you've got your camera pointed at the Great Orion Nebula right now. So
we do. Yes. Let me go
see if we can share that.
Okay, so got this. All right, let me know if you see the screen.
We do not.
Not yet, but
Oh, there you
there it
go.
is.
Oh, there it is.
Oh, okay.
Looks
There it
great.
is. All
Looks
right.
great, man.
This is great. Yes.
Yep.
Okay, so this is the Great Orion Nebula. It's a huge cloud of gas and dust. It's about 1,350 light years away, give or take. And it is a star forming region. This is a cloud of gas and dust that is slowly condensing. And as it's condensing, new stars are forming within the cloud. Now, you see 4 stars clustered together at the center. Those are 4 stars we call the trapezium. Those are very hot, very young, very massive stars that formed from the cloud. They were actually originally embedded within the cloud, but these stars are so hot and they generate so much energy that it's actually pushing the gas away from the stars, creating a pocket within the cloud. So these stars are very massive. They're the type of stars, they burn extremely bright and extremely hot, but they don't last very long. That's a characteristic of massive stars. They burn hot, they burn fast, but they don't burn very long. So just as a comparison, our sun is already 4.5 billion years old, and it's going to be around for at least another 5 or 6 billion years. These bright stars that you see in the center in the trapezium, these stars, they'll be lucky if they make it to 100 million years of age. So they just, stars this big and massive and hot just don't last very long. They burn through their fuel way too fast. But surrounding those stars is this cloud, and you can clearly see that this is a cloud that is kind of surrounding the 4 stars. And this cloud is condensing, and embedded with it, within the cloud, are many, many more young stars that are just still in the formation process. They're still surrounded by a cocoon of gas, slowly condensing and forming these lower mass stars that will eventually become like our sun or similar in size to our sun, and those will be the long-lasting stars.
Gerald, is it safe to say that some of those new stars are also forming inside the areas that appear dark?
Yes. Yeah, the areas that appear dark only because of that's a portion of the cloud that's between us and the rest of the cloud. So it's being lit on one side by those 4 stars. Those 4 stars are putting out a tremendous amount of ultraviolet radiation. And the ultraviolet radiation is going out and it's hitting the cloud, and it's exciting the atoms in the cloud and ionizing the cloud, which causes the cloud to glow. But the side of the cloud that's away from the trapezium, that side is not being hit by so much radiation, so it's not glowing. So if you see kind of up to the upper left there, there's a dark region there. That's a portion of the cloud that's closer to us than the rest of the cloud, and therefore looks dark. It's on the kind of the upstream side of the light coming from the trapezium.
We got a couple questions.
Okay.
I want to, and I also wanted to point something out. I had a hidden agenda in asking you about the dark areas of the Orion Nebula and whether there are stars forming in those pockets. And the big news story of the month, of course, is the James Webb Space Telescope.
Exactly.
And the James Webb Space Telescope, you and I are
I was
thinking
just
along
gonna
the
start-
same lines. Right. That's what happens when we hang around each other too much.
Really.
So the James Webb Space Telescope is designed to penetrate those dark clouds and see what is inside or behind them. Because even though we can't see the red, green, and blue light from those newly formed stars, we can see infrared light. And these objects that are embedded in the clouds are emitting a great deal of infrared light and heat energy, right? So the James Webb will be able to penetrate parts of the Orion Nebula that we've never been able to see by eye or by telescope in the past.
Yeah, that's going to give us a much better handle on the actual star forming process, where we can actually see stars that are in various stages of the very earliest phases of their formation. Like I said, stars that are still within a cocoon of gas. They haven't started the fusion process yet. They're getting hot, which is why we see infrared radiation coming from them. But they haven't actually started the fusion process. And so we're going to be able to actually look into those cocoons of cloud cocoons and see that very young protostar that's just in the process of starting to form and starting to turn on. So that's one of several missions for the James Webb Space Telescope.
All right. So here's a couple of questions. So first of all, Erica, you mentioned that Sotheby's is auctioning off the largest black diamond ever found, and they say it is an extraterrestrial diamond. Have astronomers or geologists really found space diamonds? This is the first I've heard of this particular one. That's very interesting. They do exist, though. Interesting. They do exist, though, because under the right conditions, various bodies in our own solar system can produce diamonds. In fact, there's a lot of speculation that deep in the heart of the gas giants, that there's so much gravitational pressure that diamonds are formed. And so in the center of Jupiter, you might find an eternity's worth of supply of diamonds, because it's got such a huge amount of gravitational pressure.
Yeah, aliens wonder at our fascination with diamonds and why we value them so much, because
they're pretty darn common.
They're pretty common.
Yeah.
In fact, there is a pretty good argument that when the universe first formed and things started to condense and cool, initially we just had hydrogen and helium, but then stars formed, and then heavier elements formed, and carbon began to form. And the first minerals to form were diamonds.
Yep.
Diamonds and graphite. So diamonds are actually quite common. Of course, most of the diamonds out in space are in the form of fine dust rather than nice little 32 karat well carved stones.
Perfectly carved, ready to be set in a ring.
Right.
Hey, Rick, did you mind if I bump you off for a second? I've got a somewhat different view of the Orion Nebula here that's worth showing. So hold on for a moment, and let me see if I can get that.
Let me stop share right there.
Oh, hold on.
Okay.
Yeah, I'm actually confusing myself on which computer I'm on.
Now,
so,
you saw that picture a few minutes ago, and you saw 3 stars in a row. And there's often a misconception. In fact, you see them again here. This is a wider view. You see those 3 stars in a row. And when people look at the Orion Nebula, especially the uninitiated, when they first look at the Orion Nebula through a telescope, and they see those 3 stars, and we tell them it's in the constellation Orion, and they immediately think, oh, those are the 3 stars in Orion's belt. Not so. In fact, everything you see in this image is just a small portion of the part of the constellation called Orion's sword. So Orion's belt is 3 stars that you can easily see with your naked eye. And south of the Orion's belt is a fainter string of stars called Orion's sword.
Now, Orion had that sword to protect against thieves who were after all those black diamonds.
Anyway, in the center of the sword, you will see what looks like kind of a fuzzy star, and that's actually the Great Orion Nebula. So everything you see here would fit if you held a soda straw at arm's length and pointed it at the belt of Orion and looked through the soda straw. Everything you see here would fit inside the field of view of that soda straw. So
Right.
this is not the three stars of Orion's belt.
Right. So what you're seeing in this view is a good kind of representation of what the Orion Nebula looks like in a dark sky through a nice wide field, Newtonian telescope. I remember the first time I ever saw the Orion Nebula with this full shape. It was astounding, and I remember it was mostly blue. So if you have a telescope, like an 8-inch telescope or a 10-inch telescope, and you point it at Orion on a night like this, you'll see this entire region in the telescope, but it will appear mostly blue. But with using a camera, we're able to get the other colors quite nicely. So anyway, I'm gonna turn it back to Rick here.
We might talk a little bit about the colors that we're seeing.
Sure.
You'll notice that there's some pink and there's some kind of a turquoise green color, almost blue color. Those colors are indicative of the elemental composition of these clouds and about the amount of energy that they're receiving from the trapezium. The pink represents the element hydrogen. In fact, these clouds are almost all hydrogen. Hydrogen, when it's ionized or when it's heated, will produce a dark red color. We call it H alpha. And it shows up quite often in astrophotography images as this pink or red color that you see. But also in this cloud is a little bit of oxygen. It's not a lot, but there's a little bit of a certain kind of oxygen. We call it oxygen 3. And when it is ionized by the ultraviolet radiation from the trapezium, it glows in a kind of a turquoise, bluish green color. And so closer into the trapezium, you see that color superimposed on the pink of the hydrogen. Now, it makes it seem like there's more oxygen there than there is hydrogen, but that's not the case. What it is that the oxygen glows so much brighter than the hydrogen does under the same conditions. And so the light from the oxygen overwhelms everything, but the actual quantity of oxygen is substantially less than the quantity of hydrogen in this cloud.
And for visual astronomers, you have to add in the fact also that the human eye is more sensitive to blue and green than it is to red.
Right.
So when I was talking about what Orion's nebula looked like through a 10-inch telescope and how it all looked blue, a lot of that was just due to the fact that my eye is more sensitive to blue than it is to the other colors that are present, but seemingly invisible at the time.
Yeah, we should also mention that we're using a modified camera, so that's why you're seeing that rich red detail in the hydrogen clouds.
That's true.
Yeah, a normal digital SLR camera would not show that pink color quite as well as this camera is showing it. This is a camera that's been optimized for this kind of viewing.
Now, for those of you who are very observant, when you look at the trapezium, which is the 4 stars in the center there, the one at the bottom, that bright one at the bottom that Rick had just put the crosshairs on, you'll see a little dot drooping down below it. And that's because it as well as the one next to it are actually at least double stars, if not quadruple. But they're visual doubles through a telescope.
Yeah, that's one of the ways.
And this one.
Yep. In this image, they just look like bumps on the brighter stars. But one of the ways we judge how good the viewing conditions are, what we call seeing, is whether or not, in looking visually through a telescope, through the eyepiece of a telescope, if we can distinguish those other two stars as separate stars, then we know we've got really good viewing conditions on that night.
Yeah, this image might be a little overexposed on the trapezium. I mean, if we reduce the exposure a tad.
Well, all astrophotographs are overexposed on the trapezium.
Yeah.
It's one of the difficulties in photographing this object is you've got this fantastic detail surrounding the trapezium, and in order to bring out that detail, you need a long exposure. But in order to not be overwhelmed by the trapezium, you need a short exposure. So really what you need to do is put together the long exposure frames with the short exposure frames, and with appropriate masking and processing, be able to bring out the best of both.
And we'll try a shorter exposure and see if that 10-second exposure coming up.
Yeah, this is one of the joys, if you will, of astrophotography is when you look at this with a telescope, with your naked eye looking through the eyepiece of a telescope, you can see the trapezium stars are nice pinpoint stars. They're bright, but they're pinpoints. But when you try to take an image with a camera, because you've got to do this long exposure, you end up with the light from those stars being scattered a little bit. And so they don't end up looking like pinpoints. They look more like blobs. And so we're always fiddling around with exposure times and ASA settings and so on, ISO settings, trying to get the optimum conditions so we can see all that there is to see in this object, in this nebula.
I think we're finally getting there.
That looks pretty darn good,
really
actually.
Good. That looks really good.
Trying to get a 5-second exposure now.
Erica just mentioned also that she's actually outside gazing at Orion now, and it's very gratifying to know that people are actually making an effort to see the things live that we show virtually, and I'm glad you're doing that.
If you have a pair of binoculars, if you look at Orion's belt, you can actually see this cloud. It's a faint little fuzzy guy, but you can see it. You've actually split the two of those stars there.
Yeah, look at that.
Yeah, look at that. Yeah, that's pretty good.
Yeah.
It's pretty good.
That's not bad for a 5-second exposure.
Yeah.
Yes, exactly.
Yeah, but now you can clearly see the two extra stars in the trapezium. So that's nice. That's nice.
We should grab a few frames of this, and maybe we can make this into a nice image for next time.
On YouTube, while you're doing that, on YouTube, somebody with the initials DL has asked a question: what is your most hopeful discovery with the James Webb Space Telescope? The James Webb Space Telescope is going to do a number of things. In addition to looking into these clouds where new stars are forming, it's going to be analyzing the atmospheres of exoplanets, planets orbiting around other stars. But one of the things that I'm most excited about is it's going to be able to look back almost to the beginning of the universe. It's going to be able to peer back probably close to 12.5 billion light years, which takes us back to just not too long after the universe formed, when galaxies were first forming, and even possibly even farther back than that, to a period called the reionization phase. And the reason it's going to be able to do that, the reason we need infrared to do that, is because objects that are that far away from us are moving away from us at a very high velocity. As I think most of you know, the universe is expanding. And one characteristic of that expansion is that the farther away an object is, the faster it's expanding away from us. And what happens is when you get out there at that 12 or 13 billion light year distance, objects are moving away from us so fast that the light emitted by those objects gets redshifted all the way into the infrared part of the spectrum. Now, what that means is that if the object was standing still, we might see white light coming from it, which consists of, red, green, yellow, blue, visible light. But when it's moving away from us at high velocity, all of that light gets shifted out of the visible range and into the infrared range. And the infrared range is actually much broader than the visible part of the spectrum. So when that gets shifted into that infrared range, we can't see it with a visible light telescope like the Hubble Space Telescope. But with the James Webb Space Telescope, we're going to be able to see that light because it's going to be in the infrared range, or the James Webb Space Telescope is tuned for the near and mid-infrared part of the spectrum. So that's going to be really exciting. We're going to learn a lot more.
And what that means from practically speaking is that will allow us to see what the very first galaxies that formed in the universe actually looked like.
Yep.
Right. What are their structures? Were they spiral? Were they elliptical? Were there populations of both? What were the star densities in early galaxies? Just all of these things that have been hypothesized but never seen. And for me, I think the most exciting part is the ability to look at exoplanets that are transiting in front of stars. That means the planet is actually crossing between the telescope and the star it's pointed at. And because that spectrograph is so sensitive, it will be able to see the spectrum of the atmospheres of those exoplanets. So we'll be able to see whether they consist of carbon dioxide or methane or oxygen, and that will give us a lot of hints about the possibility of life on exoplanets.
Yeah, we might even find an exoplanet with smog.
Yeah, yeah, that's right.
Oh my God.
Oh, thank goodness. We now have an unlimited source of smog.
Yeah. And that's actually one of the things, this is going to be a long mission. It's going to be 10, 12, 15 years. And there are a lot of exoplanets out there. So that's going to be an ongoing part of that mission for almost the entire lifetime is, trying to analyze the composition of the atmospheres of exoplanets. And that's going to be pretty exciting. I'd say that's almost on par with seeing the beginning of the universe. Okay.
Thanks for that explanation.
Yeah.
That was very good.
Well, where else should we go here?
Well, we have several options tonight. Since we're in the neighborhood, if you want to, we also have M79. If you want to look at a globular cluster, I believe it's high enough. That's in Lepus.
Yeah, it should be. Yeah.
Yeah, that way we can look at a globular cluster tonight. And the other thing I was thinking about was, since we were talking about different elements and carbon forming, it might be fun to look at Heinz Crimson Star.
Oh, yes.
At R. Leporis. And I have the Hipparcos number if you need that, Gerald.
Okay, well, let's go to the globular cluster first.
Okay.
I think it's going to be high enough here. So that's M79, right?
M79, that's correct.
And actually, before we go off, why don't we double check our focus here?
It looks pretty good to me.
You think so?
Yeah, looks,
Oh, yeah. The fact that you can split those stars.
Okay.
yeah, that was kind of the proof.
Okay, you're in live view right now, so take her away. And you're
All
going
right.
to
No,
M79?
it's pretty low, but let's give it a shot.
Yeah, we'll see. I don't.
All right. Rick, you gotta switch to
Yeah, I see something there.
shares.
Oh.
So someone on YouTube has asked the question, what is an exoplanet? An exoplanet is a planet orbiting another star. And over the last 20, 25 years or so, there's been a lot of work discovering planets orbiting around other stars. If you were around in 1990, we didn't know of any planets orbiting around other stars, but today we actually know of thousands. Of them.
Yep.
And so that's when we're talking about exoplanets, that's what we mean, planets around other stars. Okay. Most of the time we see those planets not as an actual ball orbiting around the planet. What we see is the effect of the planet. And there's two ways we can see that. If the planet, as it orbits around the star, happens to pass between the Earth and that star, the planet will block a little bit of the star's light. And by measuring how much of the light is blocked by the planet, we can get a pretty good idea of the size of the planet. And by measuring how long it takes the planet to pass in front of the star, we can get a pretty good idea how far away from the star the planet is orbiting. So that's one technique. And then another technique is called the Doppler shift technique. And that is a planet that orbits a star that's where the planet has a lot of mass and the star is or the planet is massive enough and close enough to the star, it actually causes the star to wobble. And by measuring the amount of wobble of the star, we can estimate the size or the mass of the planet and how close it is to the star. So those are the two main techniques that have been used over the last 25 years for discovering exoplanets. And like I say, we're now up to thousands of them. And that was helped a lot by the launch about 10, 12 years ago of the Kepler mission, which was a space telescope specifically devoted to looking for exoplanets. And it found a lot of them.
So the image I took looks like it's polluted by satellites.
At your image there?
No, that's not mine. That's Rick's.
Yeah.
Mine looks very different.
So the Starlink system is messing us up, huh?
It's working.
Okay, so this is M79, which is a globular star cluster, one of about 150 globular star clusters that orbit around our galaxy. These clusters orbit in a region of the galaxy called the halo of the galaxy. So if you imagine what the galaxy looks like if you were outside of it, it looks like a flat disk with a central bulge and spiral arms in the disk. But what you don't at first realize, but you'll see as you study it a little bit more, is that surrounding all of that is a more or less spherical a kind of hazy region where there's a lot fewer stars, but that's where the globular star clusters are. And the globular star clusters orbit around the galaxy in the halo. So they are away from the spiral arms, or away from all the gas and dust that's within the spiral arms. And so all of the stars in these globular clusters are extremely old, more than 10 billion years old. And these stars, the stars in the cluster orbit around the cluster. And then the cluster, like I say, is orbiting around the galaxy. And the stars that are orbiting around the cluster, they orbit in highly elongated elliptical orbits. So they go in close to the center, and then they swing way out. And as they come out, they slow down. Eventually, they drop back in and come back in and speed up as they approach the center, whip around the center, and then back out again. So because of that, it tends to look much denser towards the center of the globular star cluster than out towards the fringes. These stars are very close together. As a general rule, if you lived on a planet orbiting around one of these stars, you're likely not to have a nighttime, because there would be so many stars so close to you all night long that you'd never get a fully dark sky. It would be like having dozens of full moons in your night sky. And like I say, there's about 150 globular star clusters like this. We're actually at a time of the year when we don't see very many of them. Later on in the springtime, we're going to see a bunch of them.
Yep.
Now, Gerald, have you mentioned the color of the stars and what significance the color of the stars in this globular cluster have?
Why, no, Rick, I haven't mentioned that yet, but since you brought it up.
Yeah, so I'm stalling for time because I want to get a couple of more episodes.
So anyway, these stars are all very old. These stars formed when the galaxy was first forming. And because they're in the halo and not in the spiral arms, they don't get a lot of new star formation going on in these clusters. So these stars are all more than 10 billion years old. Now, most of the really massive stars, the stars that would shine really bright and bluish white in color, those stars have long since died away. Those are the stars that only last a few 100 million years. But the low mass stars, the stars that are the mass of our sun or even less, those are the stars that last for billions of years. So most of the stars that you see in a globular star cluster like this are going to be kind of yellowish white, or even red. But what's interesting is every once in a while you see a blue star within the globular clusters. And that puzzled astronomers for a long time, because they knew all these stars were extremely old. Stars are only blue if they're very massive and very hot, but massive hot stars don't live very long. So how can you have a 10 billion year old blue star?
Yeah.
Well, the answer is because these stars are so close together, they bump into each other every once in a while. And when that happens, there's a couple possibilities. Either the two stars merge to form a single, much more massive star, so you sort of reset the clock, if you will, or one star strips away the outer layers of the other star, exposing the much hotter interior of the star. So when we see these blue stars within what should be just white and yellow stars, we call those blue stars blue stragglers. So, okay, Rick, I've killed some time here.
That's what I call myself when I'm walking up a hill.
A blue straggler.
A blue straggler. All righty. Okay.
That begs the question, which somebody asked, not just me. when we're looking at these globular clusters and we're making these estimates of age, how do we know that these stars are the age that we think they are?
Good question. There's a variety of techniques that we use. If we see a star that's yellow in color, and when we look at it spectroscopically, if the absorption lines, when we look with a spectroscope at a star, it splits the light from the star into various colors, and depending on the elements within the star, we get what we call absorption lines. They're little lines that we see in the spectrum of the star. And if those lines are very narrow, that means the gas around the star is not very dense. But if the lines are very broad, that means the gas is very dense. So a star that is young is going to have very dense gas. It's going to be very compact and it's going to be very dense. And so you would see broad spectral lines. But a star that's very old, the gas has expanded. Gas around the star has expanded. And so it's thinner, it's less dense. And so the lines will be narrower. And so that is one of several techniques that you can use to judge the age of stars. We can also judge the age of stars by how bright they are and by their color. If we can figure out the distance to them, the age of the star and the color of the star and how bright it is all a function of the age. So there are several different techniques that we use to estimate the age of stars.
Yeah, Gerald, I was just looking at the image here, and you can see the tight core of the cluster, and then there's kind of a semicircle of stars. I kind of wonder, are these foreground stars, or do you think they're part of the cluster?
I suspect that most of them within, say, the circle that you're drawing right now are probably part of the cluster.
Huh.
But I would say some of them are definitely foreground stars. So it's probably a mix of both.
I see. Okay, this has got a mind of its own. It's still imaging. We can move on to another object anytime.
Well, there's a question came up on YouTube. Have we found any exoplanets that may have a good chance of supporting life? Well, that's one of the reasons why we're so interested in James Webb Space Telescope. We find exoplanets in the part of their solar systems where it's possible that they support life because they're the right distance from their parent star to where liquid water could exist on the surface if it has a reasonable atmosphere. So we call that region the Goldilocks zone or the habitable zone around stars. And we have found exoplanets that are the right size and within the habitable zone. So in that sense, they might harbor life. But because we have not yet been able to actually analyze the composition of their atmospheres, we don't know that they actually have a good chance of harboring life or not. So that's one of the reasons why we're so interested in what the James Webb Space Telescope is going to be able to do.
Good question. Stephen asked a good question too, which is how durable are the mirrors of the Webb telescope from micrometeorite impacts? And the answer is both durable and not so durable.
Yeah.
So the durable part is the substrate, which is beryllium. These are not mirrors made out of glass like the Hubble telescope, which was a glass mirror. The James Webb telescope uses beryllium instead of glass, and that's because it's a very light and very durable material. But the coating on that on those segments of beryllium is gold, And the reason it's gold is because gold reflects infrared light at a much higher efficiency than any other type of coating. So the coatings can be damaged most certainly by micrometeorites. I think that the beryllium substrate would probably survive a lot of abuse.
Yeah. So what's going to happen over time? You're going to get some pitting of the gold surface on the mirrors, but it actually would take a lot of pitting to really affect the quality of the image that we're going to get from the James Webb Space Telescope. We amateur astronomers, we use telescopes all the time that use mirrors. A lot of those telescopes have open fronts, so dust can get inside and get in on the mirror. And you'd be surprised how much dust accumulates on the mirror before it starts to affect the quality of the image that we see with those telescopes. And the same thing is going to be true for the James Webb Space Telescope. Yes, over 10, 15 years, there's going to be pitting of those gold surfaces, but it's going to be a long time before it's going to adversely affect the quality of the image. That said, James Webb Space Telescope is orbiting out at a Lagrange point. It's orbiting around the sun in an orbit that parallels the Earth's orbit. And there are near-Earth asteroids out there. And some of those asteroids are fairly big. And so there is always the possibility, it's a very, very small possibility, but it's not zero, that the James Webb Space Telescope could get hit by a space rock, and that would not be good at all.
You might say those odds are astronomical.
Yeah, there you go.
Very good. All right. So next, do you want to, since we were talking about carbon and diamonds and stuff like that, how do you feel about slewing over to Arloporus?
All right.
I don't know how you search for it on that software.
Probably need an NGC number or a SAO. No,
I have a Hipparcos number. Does that work?
Okay, go ahead.
It's 2320.
2320. Mm-hmm. All right. How far away is that from where we are here? Okay, we're slewing. Whoa, that's pretty far over there.
It is, yeah. I guess it wasn't that close.
Yeah, I'll tell you what, let's do this. Let's go to a bright star first.
Yeah.
And sync on that, and then we can slew to. Okay, I'm slewing back. Are you in live mode? Yes, you are.
Yes, I am.
Yes, you are. Okay.
Yeah, sorry about that, Gerald. I got a D in distance.
It's actually not too bad. Okay, we'll try that one more time. Okay, so what we just did, our telescope is computer controlled, and it's capable, it has a very large database, and it's capable of pointing to any object that's in the database. All we gotta do is ask for it. However, when we make big moves like we just made across the whole sky, although the telescope tracks pretty well. It doesn't track perfectly. So what happens is when we make these big moves, when it arrives at where it thinks it should be, it's not quite there. And so we have to resynchronize the system in order to get it very accurate in that part of the sky. And that's what we just did. We moved to a bright star, centered it up, told the computer where the telescope was pointing, and then we were able to get to our crimson star, which doesn't look very crimson.
It might be on the brighter part of its cycle right now.
And
Let me see what we got.
did you
here.
just change
I
the
did.
focus?
Yes. It's actually looking pretty good right there.
Yeah, that's pretty good focus,
Okay.
but not very red.
Not very red tonight. So
Yeah.
Well,
So this star, this Heinz crimson star, is what's known as a carbon star, and it's also a variable star. When I say a variable star, it means it gets brighter and dimmer over time. And the cycle for this particular star is about 400 days. So it's been over a year for it to go from its brightest point back to its brightest point. And the magnitude difference from its dimmest to brightest is somewhere around magnitude 5 at its brightest and magnitude 11 at its dimmest. So it's a pretty extreme variable star. And the reason it's so red, there's a couple of reasons. First of all, carbon has, when it's glowing, has a reddish spectrum. And so it appears red from the carbon. But probably more significant is that the outer shell of the star consists of a large amount of carbon. And that carbon is probably blocking the blue or white light that is being generated farther inside that star. So it's actually like having a red shade around a lamp, is a way to think about it, with the shade being carbon. So here you can, in that last image, Rick, it kind of looked like, oops, I'm having
yeah, I'm having an issue with your audio. Gerald, can you?
Yeah, I'm not hearing you at all, Rich.
Yeah, Rich, there's you got an issue with your audio. Maybe move your mic or something.
No, it's not what it is. It disconnected from the internet.
Oh, yeah, that happened to me earlier. It's the perils of live presentations over the internet and Zoom and yeah, and Wi-Fi.
Okay, so while Rich is getting himself reoriented here.
Can you hear me now?
Yeah, now I can hear you. You know, is the crimson star, is it this one?
Yeah, it's that one
Down here? Or the
Yes.
It's
Yeah.
that one. Okay. Okay.
Yeah.
That's
And
definitely
it's
looking
pretty
brighter.
obviously
I was
red.
looking at the,
Yeah.
okay. Yeah, obviously. In fact, let me reduce exposure a little bit here.
So what I was saying when the Wi-Fi so really cut me off was that one of the reasons that the star might appear red is that the carbon shell on the outer layers of that star is blocking the white light or the bluish light that would be coming from the star if it didn't have all that carbon. And so it's actually acting like a filter.
All right. It's a little bit more reddish now. Yeah, that looks pretty good. Yeah.
Well, he took out his crayon.
A little touch-up here.
I
and
saw
there.
him do it.
It's a-
You
it's
a-
couldn't see it from where you
It's
were.
amazing what a magic marker can do. Yeah, I just turned the red lights for the star on. Yeah.
So basically, this is a dirty star.
Yes, it is.
It's churned up a bunch of carbon, and the carbon is absorbing a lot of the light, and so it makes it look this crimson or reddish color. It's not really crimson, but it definitely has a reddish orange color. And there's about a gazillion messages on YouTube here saying we can't hear you.
Yeah. Yeah. Sorry about that, everyone.
Yeah.
We're subject to technical failure like the best of them. So this is a funny question. If you guys are amateurs,
I see that.
Yes.
who are the professional astronomers? Well, my answer to that question is the ones who are able to get grant money
Yeah.
and telescope time on large instruments. And have PhDs in the field.
Yeah.
You know, as I recall, it's the professionals work 9 to 5. It's the amateurs that work at night. Yeah.
Yes.
Yeah, the professionals are the guys who sit in nice, warm control rooms far away from the observatory,
Right.
watching images on their computer screen. Amateurs actually sit next to their telescopes and watch the image on the computer screen, and the amateurs are the ones who are freezing because they're outside sitting next to
This
Yes.
amateur just had to put on a jacket.
And we need to sit next to our telescope so we could curse at them loudly,
Yeah. Yeah.
because that's what ends up happening when things aren't working. But also, professional astronomers, they're really studying the data that comes back from all of this instrumentation that we've been talking about. So they're going to be doing things like looking at spectra and looking at light curves over time at stars. And depending on how the light curve might change, you could say, well, that curve is changing because it's a variable star. That curve is changing because there are exoplanets that are transiting in front of it, all these possibilities. And what they'll do is tease apart the data and run various statistical analysis on it in order to reach conclusions about individual stars or populations of stars.
That said, amateurs and professionals often work together. This is one of the sciences where a lot of amateur astronomers have equipment that rivals what's available to professionals. So it is very common for there to be professional and amateur astronomers collaborating on certain science projects. One of the nice things about an amateur astronomer is an amateur astronomer can sit at their telescope all night long looking at one object. Professional astronomers who have to sign up way in advance for a certain amount of time on a telescope, they may only get an hour's worth of observing time on that telescope, which they've reserved, weeks in advance. Whereas the amateurs, they can sit there all night looking at the same object, collecting a lot more data. So the main difference between amateur and professional astronomers is the pros get paid and the amateurs pay.
Yes, that's an apt description.
We pay.
That's right. There's another question. What are all the components of a Goldilocks zone? Well, I think the most important component of the Goldilocks zone is a complete absence of bears, wouldn't you say?
Oh, gosh.
But it would be the temperature of the star. Because, imagine if we were orbiting a star that was, 4 times the size of the sun, right? We'd be getting way too much sunlight. It would be very hot and uncomfortable. The orbit has to be in a zone that is fairly free of debris, right? And like the Earth happens to be in a fairly good debris-free zone, even though we have near-Earth asteroids. We're not like going through, clouds of rocks all the time. Some of the planets further out have a greater chance of impacts than the Earth does. So that's another one. Also, where in the galaxy is the star that planet is orbiting? Is it near a very high and dangerous energy source? Is it getting bombarded with alpha radiation or something like that from a nearby neutron star? And all of those things together determine whether it's considered to be in the Goldilocks zone. So there's a Goldilocks zone within the solar system. There's also a Goldilocks zone in the Milky Way galaxy itself.
Yeah. So if you guys don't mind, I'm going to slew to a star and sync on it, and then I'm going to take it to a planet. We actually do have planets up. So
I'm going to guess you're going to one that starts with a U.
You're absolutely right. You are absolutely right. We're going to go to the U star. Only it's not pronounced U, it's pronounced ooh.
Ooh.
Ooh. And Rick, if you can go into live mode, please.
You are in live mode right now.
That's not what I see.
That's what I see.
Oh, wait, I'm just because I'm looking at the wrong screen here, you big dummy.
There we go.
Yeah, we're all doing that tonight.
Yeah. All right, hang on
Don't
just a
feel
second
bad.
here. Let me do a little
That looks like a double star.
yeah, I'm just using it to sync the telescope.
Okay.
And then we're going to go to the U planet. And maybe. And here we go. On the way.
Stephen, you're asking a lot of good questions tonight. He was curious if Nellie captured any observations of the large meteor the size of the Empire State Building that recently missed Earth, as in Tuesday night. And unfortunately, we were clouded out.
Yeah, we were actually planning to image that asteroid, which would have been
And we were going to show you a little video of it tonight.
Yeah, we had great plans, but Mother Nature had other plans.
Yes.
So what happened there? I thought I was seeing it.
Well, we're in live view, so we're going to take an image and see if we can get a better image of it. 5-second image. Coming up.
Right.
All right, anytime. There we go.
Yeah. So
Oh,
are we
there we go.
off by that much, or
Let me see if we're zoom out. No,
no?
we're done.
Okay, we're
That's
good.
not bad.
Okay,
It's just that
okay.
it was off center.
So if you look at this thing,
software.
you might notice it's not really a star. It doesn't have that nice pinpoint of light like a typical star. This guy has got some actual structure to it. This is the planet Uranus, what some of you called Uranus. It's actually known as Uranus. Uranus is the seventh planet. Yes, seventh planet from the sun, seventh full-size planet from the sun. And it is well up in the sky right now. It has, you can't see it very well in this image, but it actually has kind of a greenish tinge to it. And that's because it has a lot of mercury in its atmosphere, or not mercury, methane in its atmosphere. It is considered a gas giant planet. So it has a dense atmosphere with clouds, and those clouds have a definite greenish tinge to them. So this is actually a pretty good image here.
Yeah, it is.
this is, typical of how we see these most distant planets, Uranus and Neptune. We don't see them as disks with actual features on them. We just see them as very small, not quite pinpoints of light, a little bit bigger than a pinpoint of light with a little bit more than the typical color to it. Neptune would look somewhat similar, although Neptune is more bluish than green in color. And then I think that little thing off to the right there might be one of Neptune's moon.
I'm seeing
Uranus.
Yeah.
Uranus.
I mean, Uranus's moon.
If it's
Okay.
one of Neptune's moons, then it's something
Then
significant happened this
Yeah,
week.
that's right.
So just to talk for a second about the name, this planet is actually named after one of the gods in Greek mythology. Uranus and Gaia were the father and mother of the Titans in Greek mythology. And so his name was Uranus, and he was the guy the Greek mythology god that this planet was named after. So he wasn't named after Uranus, and he wasn't named after Uranus. He was named after Uranus.
So it's an interesting planet too. So if you're wondering about the length of its day and the length of its year, it takes 84 Earth years to complete its orbit of the sun. So 1 year on Uranus is 84 years on Earth. The day is 17 hours. Now, what I find most interesting about it is the tilt of the planet is such that it appears to be rotating on its side with respect to the sun. So the axis of rotation, one side of that axis points at the sun. So the whole thing is kind of spinning on its side, like a top that has almost fallen over.
Well, it only points towards the sun for 1/4 of a year. So the North Pole points at the sun for 1/4 of a year. Then the equator points at the sun. Then the South Pole points at the sun for 1/4 of a year. Then it's the equator again. Then you're back to the North Pole. So it makes one complete rotation relative to the sun, but it's the poles that are rotating almost parallel to the direction of its orbit. It's completely different than any other planet in our solar system. And we think it's because at some time early in its formation, it collided with another object and basically got knocked over on its side.
Yeah. But you could, if you've ever played with one of those gyroscopes, you can kind of imagine what that would have looked like. You give it a whack and it tilts onto its side and still spins.
All right.
I think we've got 3 moons that I'm looking at. Titania, that one.
I think you're right.
Yep.
And then Oberon is this one. And then this very faint one. No, that's a star. But there's several others, including Ariel.
I don't see that. Well, yeah, okay, maybe there, yeah.
I think actually Umbriel. This is, I think Ariel and Umbriel are these two right here. It's probably very difficult to see.
Oh, but, okay, yeah.
So there's 1, 2, 3, 4, 5 moons in the frame right here. And one, I think that's it.
Yeah, that's pretty good.
To give you some sense of the size, the volume of Uranus is 63 Earths.
Wow, it's huge.
Let me help you with the pronunciation. What's the name of the communications officer on the Starship Enterprise, the original Enterprise? Uhura, right? Not Uhura. It's right. Uhura, right?
It's falling on deaf ears. I'm
Uranus.
sorry, Gerald. Uranus.
Uranus.
I have never pronounced it Uranus in my entire life, so I'll
Oh.
work on that. We should take a vote.
Yeah.
It should be a
Yeah,
YouTube
no.
a YouTube challenge. Is it Uranus or is it?
Yeah. Well,
I was
it all
once
like.
with a large group of amateur astronomers, and I challenged everybody to come up with unique pronunciations. And a lot of fun was had by all.
I'll bet. All right. Well, we're a little past 10 o'clock here. Anything
Yeah.
else we want to look at? Any other questions that we need to be answering?
You know, I might suggest maybe a look at the moon since it's lighting up our.
Oh, that's right. It's
Yeah, it is.
behind
Oh,
us. Well, we
well,
can
there we
end,
go.
end on the moon, right?
Let's
Yeah.
do it. We'll end on the moon, and I'll put it. We'll get a wide field view as well as the lunar lander view.
I advise you guys to change your ISO settings.
Yes.
Oh yes, okay.
Good advice.
Yeah, so I'm going to manually slew here for a little bit. Watch your cables.
Oh,
Yeah.
God, yes.
Yeah, my camera became disconnected. I have to restart it.
I'm going to go a little farther here, guys.
I had this problem earlier.
Going just a little bit farther.
That's fine. My head's out of the way.
Okay.
All right, let me see if I can connect up again.
So the bright star you're seeing on your screen right now, that is the star Regulus. It's the brightest star in the constellation Leo.
Oh yeah. That looks good.
All right, you guys got your ISO set and everything set here because it's going to be bright.
Yeah, I should set it to something lower than 25,600.
I think so. Yeah, like maybe 100 or something.
yeah. I'll go to 100. That's always a safe bet.
Rick, are you ready to?
Oh yes, go right
All
ahead.
right. Okay. Here we go.
Ah, it burns. That looks pretty good.
All right, let's see live view.
Ooh,
Wow! All right,
you
That
found the
is
moon.
gorgeous. Yeah,
We found the
we
moon.
found the moon. Yeah, this is amazing.
Well, I've discovered some dirt on my sensor.
Let me zoom out. I don't know, I guess.
So that crater that you see just to the right of center with the central peak in it, that's the crater Theophilus. If you look at that large dark area that's up above the center and off to the right, that's Tranquility. That's where the Apollo 11 astronauts landed.
You want to go to the wide field?
Yeah, we could if you want to. Hold
Yeah.
on for a moment. Let me put it back on frame and focus. Share screen.
That's actually a pretty doggone nice image, boy. I'll tell
Isn't
you.
it though? Yeah.
Whoop. What happened?
Now you got a wider field.
We've been hijacked.
Oh. You couldn't reduce it even a little bit more, like exposure time or ISO or something like that? Because you
Oh yeah, no, it reset itself back to a ludicrous ISO. Get that down
I
to.
thought it was automatic. It doesn't it read?
Yeah, it drives me nuts actually that it does that.
No, I think your camera is doing automatic exposure setting.
Yeah, problem is this zoom window keeps getting in the way. Hold on for a moment. Go to 180 second. Too
Okay,
dim.
There we go.
Second. All right, there we go.
Oh, there we go.
Yeah,
That live view?
that's live view.
Okay. Yep. A little too bright now.
All right,
Not too bad though. Not too bad.
Yeah,
I like that view.
It did reveal some streaking on my sensor here, which I've got to deal with.
I thought that was a new blemish on the moon.
Yeah.
I was going to say, what is that?
It was that Empire State Building asteroid. It fell on its side and landed on the moon.
Yeah, thought the asteroid.
Nonetheless.
Yeah. Well, let's go back to the.
Yeah, go back to your review.
Other one, yeah.
You have less gunk on your camera.
Let's see, where is it?
I have to find that now.
Oh. So way up at the top of this image, right at the terminator, which is the boundary between the light and the dark area, you see two side-by-side craters. Those are Atlas and Hercules. And then directly below them, that's the Sea of Serenity, the round one right there. And then below that, let me slow down a little bit. Below that, to the right a little bit, that big open area, that's the Sea of Tranquility. Now, I want you to notice something. Notice the color of the Sea of Tranquility versus the Sea of Serenity up to the left there. Notice the difference, how one is darker than the other. And if you're really sharp-eyed, you may notice that Tranquility has a slightly bluish tinge. Both of these are what we call impact basins. They're large impact craters, very, very old impact craters that subsequently filled with lava. These impacts cracked the crust of the moon back 3.8 billion years ago when the moon still had a molten interior. And lava oozed up through cracks in the crust and filled these basins. But what's interesting is the lava in the Sea of Serenity is different than the lava in Tranquility. The lava in Tranquility has a much higher titanium content. So if you want to go mining titanium, the moon is the place to go.
Well, what do you think about diamonds?
Might be.
Well, titanium and diamonds, yeah.
Yeah, there you go.
Well,
you know, I hadn't really noticed the color difference before on those two seas. You know, you can actually see that bluish gray color of Tranquility. Yeah.
Yeah. If you use the right filters, you can really bring out that bluish color of Tranquility. It's quite pronounced, you know.
And actually see it all. I don't know how the view is on YouTube, but you can see it right around here.
Right. And you can actually see a kind of a border between the two where it goes from lighter to darker.
yeah, that's easier to see the difference.
Right
right
there
at the dividing line.
Right there.
Yep.
Yeah, that's an amazing view tonight. Yeah.
Yeah, this is really good viewing conditions. So anyway, we have found the moon.
We have found the
Yeah.
Still
moon.
there. And it's in the eastern part of the sky. So if you go outside right now, if you're here in the Bay Area or anywhere on the West Coast, you'll see it in the eastern part of the sky. And if you take a pair of binoculars and look through them, you might even be able to pick out some of these craters.
All right, gents.
Well, I think
This was a very successful night,
yeah,
It was,
yeah.
and it was fun.
This is the best viewing we've had in a
In a
long
long
time.
time,
So
longer than
Yeah,
I care
yeah.
to think.
Yeah, really. So we're going to do this again next month on the third Thursday of the month in February, and again at 9 o'clock at night on the third Thursday. I forget what the date is, but if you want to join us again, then we will be looking at some different objects, probably some more globular clusters, and a few other objects, maybe a nebula or two. So join us then.
join us on Thursday, February the 17th.
Oh,
Yes.
thank you. There you go.
That's
All right.
total service package. Here.
Okay. So might check to see if there are any more questions. How
Yeah,
tall are
take-
these craters? Well, Atlas, the crater depths run between 3,000 and 5,000 feet for a lot of these craters. And some of them are even deeper than that.
I wonder what Tycho would look like, or the Clavius crater tonight.
It's kind of in the brighter part, but you can slow down if you want to. Hang on a second here.
Sure.
I gotta switch back. I'm switching back and forth between YouTube and Zoom. So we'll come on down here. I can see the rays from Tycho.
Oh,
So there it is.
Yes, that's
There's
Tycho.
Tycho right there. Tycho is a relatively young crater. Tycho is right around 100 million years old. And when this impact occurred, material was thrown up out of the crater and actually cast hundreds of miles away from the crater. In fact, I think one of these rays is over 1,000 miles long. And this is just ejecta from the crater itself. Okay. Well, I think it's about time for us to say goodnight.
Yep.
And we appreciate
Well, thank you
everybody
guys, and
tuning in.
thanks
Yeah, it's been
thanks to
great,
everybody who attended tonight. We had quite a few viewers, and yeah, keep up the excellent questions, and
We
we'll
will
be here to answer them.
see you on the 17th of February.
We
All
will
right.
look forward to it. All
All
right.
right.
Well, good
Good
night,
night.
everyone.
Night, everybody.
Good night.